Let's continue looking at the trends on the periodic table. We're going to introduce electronegativity today, and that's just a measure of the ability of an atom in a bond to attract electrons. Atoms are assigned electronegativity values, and those with large values will attract shared electrons more strongly than atoms that have small electronegativities. The electronegativity actually decreases down a group. So if we have our periodic table, electronegativity decreases down a group and increases as you go across a period from left to right. So if you can remember fluorine in the upper right-hand corner, that's going to be one of your most electronegative atoms. The decrease in electronegativity down a group happens because the electrons in bigger atoms are held less tightly. Remember, they have larger radii. So if it's larger radii, the distance is increased between the nucleus and the valence electron, and it's not going to be held as tightly. So the electrons in the inner energy levels tend to block the attraction of the nucleus for the valence electrons. It's called a shielding effect because it shields the attraction of the nuclear charge from the electrons. So here is a picture of all the trends. And this is helpful, especially when you're taking your quiz, until you get to know these integrally as you're learning to memorize them and to understand the trends. So the atomic radius increases as we go down a group and increases from right to left. Ionization energy increases from left to right. Electron affinity increases from left to right. Electron affinity decreases if you go down the periodic table, but increases if you go bottom up. And we're not going to talk about metallic and non-metallic character right now. So let's do some practice questions. I want you to try these questions and then come back and answer them on your own, or see if your answers that you answered on your own are correct. So as we move down a group in the periodic table, what happens to the size of atoms? Does it increase, decrease, stay the same, or first increase and then decrease? So we're going down a group. You look, as we go down a group, we know the atomic radius increases. Now, what general trend is true across a period for ionic radius of cations? So as we go across a period, we know that the ionic radius decreases as we go across the group, or as we go across the period. That is something from last lesson, but it is still important for us to keep in mind and review. Which group on the periodic table typically forms the largest cations? Is it group 1, group 17, group 14, or group 18? Well, we could look at this. If you said, well, I'm not sure, well, we know group 17 gains, so it doesn't make a cations. Group 14 don't typically make charges at all, make ions. And group 18, they're not going to make cations. It's group 1, the alkali metals. If it were between group 1 and group 2, it would still be the group 1 alkali metals because we know that as you go from left to right across the periodic table, the size decreases. Okay, so let's look at these questions. Again, I want you to try to answer them and then come back after you've answered them and check your work. Which factor has the greatest influence on the size of an ion? Is it the type of a chemical bond? Is it the number of valence electrons? Is it the nuclear charge and number of electrons? Or is it the number of isotopes? This again carries some information from the previous class. And so it's not going to be the type of chemical bond because that doesn't have any bearing on the size of the ion. We have the number of valence electrons, the nuclear charge, and the number of electrons, or the number of isotopes. Well, we know that the nuclear charge is the number of protons in the nucleus, and that does have an effect on, on the size of an ion, because if you have more protons than you do electrons, then it's going to be held tightly and it's this radius of the ion is going to get smaller. But if you have less protons than you do electrons, then it's going to be held more loosely and it's going to be larger in size. Now, which of the following ions has the greatest number of electrons? For this, we'd have to look at the periodic table. So let's go to the periodic table. Let's look at sulfur. Sulfur has 16. So if we come back here, and we know that sulfur has 16, but it has 2 minus, which means it's gained 2. So that'd be 16 plus 2 equals 18. So now let's look at our chloride ion. So chloride has 17, but it's a 1 minus charge. So chloride is our 17 plus 1 equals 18 because it gained 1 electron. So let's look at potassium here. Potassium has 19 electrons, but it's a K plus, which means it's lost 1. So this would be 19 minus 1, which gives us 18. So now let's look at calcium. Let's look at calcium. Calcium is here, and it's lost 2 plus, or it's 2 plus. So that means it's lost 2 electrons, which means it's at 18. So these are all the same. So it should actually be none of the above because if this was at 20 and it lost 2, it's at 18. So the answer would be none of the above because they all have the same amount. That was a little trick question. All right. Let's look at the next part. Now, in period 2, we have metals, metalloids, and nonmetals. Boron, which has the symbol B, can act as a metal and form a positive ion, or it can act as a nonmetal and share electrons. More often than not, it acts as a nonmetal and it shares its electrons, but there's something special about boron. It only has the capacity to share 3 pair of electrons, so it can't achieve an octet. So boron is an exception to the octet rule, like hydrogen and helium. Only it just can't form an octet. Let's talk about what happens in each group. So here we have alkali metals, and they're the metals that are in group 1. Their properties are soft, silvery white metals, and they're good conductors of heat and electricity. They react by losing their s-valence electron. The most reactive alkali metal is the one that has the least attraction for this electron. So think about what element this would be. What element in that group would have the least attraction? Remember, the farther away the electron is from the nucleus, the less attracted it is. So this would be francium, because francium is the largest element in that group. So francium, therefore, would be the most reactive because it has the least attraction for that electron. Lithium is the least reactive because it has most attraction for its valence electron. Now, because of their valence or their chemical reactivity, alkali metals don't exist as free elements in nature, and they're only found in compounds. Lithium is still very reactive, but it's not as reactive as francium. To separate sodium from chlorine, for example, you have to pass an electric current through molten salt through the process of electrolysis. Electrolysis is how we separate hydrogen and oxygen in water, but you'd also have to do that in sodium and sodium chloride, which, remember, it has a melting point of 800 degrees Celsius. So that is extremely difficult and takes a ton of energy to do that. In group 2, we have the alkaline earth metals, and they have similar properties in group 1. They're only found in compounds in nature as well. They're less reactive because they have to lose 2 electrons instead of the 1. These metals are denser and harder, and they have higher melting points than the alkali metals in group 1. The reactivity increases with size of the atom for the alkaline earth metals as well. The farther away those valence electrons are from the nucleus, the less attracted they are to them, which means the more reactive they are. Beryllium is important for the nuclear weapons industry, and alloys of magnesium are used in things such as jet engines, where we need lightweight, strength, and corrosion resistance. You don't want your engines to rust and fail, for sure.